In this video, we're going to talk about the equilibrium condition. What does it mean to say that a reaction is in chemical equilibrium? Some reactions go all the way to completion. That means everything that was once a reactant will become a product given enough time. So we don't presume that it goes quickly. It's just that eventually everything becomes a product. But most reactions would stop far short of this, and they are said to be reversible. What we mean is reactant molecules can become product molecules, but also at the same time, product molecules are going back to become reactant molecules. It's not just a matter of giving a reaction another hour to finish its work. It's that it would never become all products. And there's something interesting about that. And in this unit, we're going to explore that. If our reaction is A yields B, we write the forward reaction with A on the left side and a reaction arrow pointing from left to right and B on the right side. But when we say the reverse reaction, we're talking about the products becoming reactants, B yielding A. Sometimes we write this with a double-sided arrow, showing an arrow going both left to right and right to left. You're welcome to do that, but most chemists just write the arrow pointing from left to right. And they want you to know that the vast majority of reactions are reversible. The forward reaction happens when reactants become products. The reverse reaction happens when products become reactants. Eventually, you'll reach a point where there's no further changes. We call that point chemical equilibrium. Now, it does not mean necessarily that the concentration of products is equal to the concentration of reactants. It just means that there's no further changes. It's the state in which the concentration of reactants and products remains constant. Please note, it's sometimes called dynamic equilibrium because individual molecules might still be reacting. Another way of putting that is that at equilibrium, we can say that concentrations of all species remain constant. And the rate of the forward and reverse reactions are equal. That is, it's not going to pick up speed going from reactant to product or from product to reactant. Everything is just remaining constant. We can represent this in a graph in a couple of different ways, and I'd like you to be familiar with these graphs. If we graph concentration versus time, that's different from a graph of reaction rate versus time. Here's our reaction, A yields B. You could write a double-sided arrow or not. In the concentration versus time graph, the concentration of B rises from 0. Presumably, you don't have any products in the reaction vessel at first. So it rises from 0 until it levels off. And the concentration of A, the reactant, starts at some high concentration and goes down until it levels off. Equilibrium is achieved when the leveling off happens. Notice the lines that represent concentrations don't have to touch each other. They might, and that's okay if they do, but that's of no particular chemical consequence. The other graph, reaction rate versus time, shows both the forward and the reverse rate. Kr stands for the reverse rate of reaction. If at first you don't have any product molecules, at the very left edge of the graph, the reverse rate is 0, but it's going to get faster as time goes on until it levels off. And the forward reaction, the one where reactants are becoming products, since you begin with 100% reactants in the reaction vessel, that's the one that's going to start out high as a rate and then go down. Eventually, these do level off, but equilibrium is achieved not necessarily when the leveling off happens, but when they touch each other, when the forward rate and the reverse rate have equaled off. So, concentration versus time graph, we know that we've got equilibrium when the concentrations stop changing. But in the rate versus time graph, they have to actually touch each other. Now, we can write this out and put numbers to it. But first, I want to talk about a law called the law of mass action. This describes equilibrium concentrations of all species in a reaction. Now, this looks like a lot of letters, and it is. I want you to focus on the capital letters A and B yielding C and D right now. Those represent the chemical species. The italicized letters J and K and L and M, they represent the coefficients. Now watch what we do here. K, which is the equilibrium constant, is equal to the concentration of the two products, C, raised to the power of its coefficient, times the other concentration of the product, D, raised to the power of its coefficient, M, all divided by the concentration of the reactant, A, raised to the power J, which is its coefficient, times the concentration of B, the other reactant, raised to the power of its coefficient, K. This might make a lot more sense once we do a sample problem with real numbers. But the idea is take concentrations of products raised to the power of their coefficients and multiply them together, put that in the numerator, and divide it all by the concentration of the reactants raised to the power of their coefficients and all multiplied together. What you get is a number that will stay constant for a given reaction. It's called the equilibrium constant. Oh, and by the way, maybe from back in Unit 7, it's helpful to point out, if you see a chemical formula with brackets around it, that means concentration or molarity, the number of moles per liter of that substance. Okay, let's take a look at a sample problem. Write the expression for the equilibrium constant K for the following reaction. 2SO2 plus O2 yields 2SO3. We're going to consider the products first, the things on the right side of the arrow. So there's only one product in this equation, it's SO3. We're going to put that substance in brackets, and we're going to raise that substance's concentration to its coefficient, which is 2. So in the numerator for the expression for the equilibrium constant, we're going to put SO3 in brackets and a 2 above that. Then we're going to turn our attention to the reactants, SO2 and O2. Since SO2 has a coefficient 2, we're going to make sure to put that as the exponent outside the brackets. So it's the concentration of SO2 squared times the concentration of O2, the other reactant. And since its coefficient is an implied 1, we don't need to put an exponent. Although if you felt like it, you could write a 1 exponent. It just doesn't change the mathematical nature of the calculation. Okay, let's take a look at this equation one more time. So A and B yield C and D. At equilibrium, the rate at which the molecules C and D are forming, so the forward reaction, is the same at the rate at which molecules A and B are forming, the reverse rate. In other words, the forward and reverse rates are equal. That's why the ratio of concentrations in the equilibrium expression doesn't change once equilibrium is reached. It's not necessarily going to be a ratio that's equal to 1, although it could be. It just means that at equilibrium, there's no further changes in concentration. Okay, let's go to a sample problem. Let me pull up my Jamboard here. Given the following reaction and the concentrations shown below, calculate the value of the equilibrium constant K. Here's your balanced equation. N2 plus 3H2 yields 2NH3. And they give us the concentration for all 3 of those substances. So let's start by writing the expression. K, the equilibrium constant, is equal to the concentration of in this equation, there's one reactant, one product, NH3, and its coefficient is 2. So we're going to make sure to square that concentration. There are two reactants, N2, that we'll put in brackets. And you'll notice that N2 has an implied coefficient of 1, so its exponent would be 1 in the expression. The other reactant is H2, and it has a coefficient of 3. Because of that coefficient 3, we need to be sure to cube the value of the concentration of H2. Now, we have actual numerical values for these concentrations. So we're going to take 0.157, the concentration of NH3, and we're going to take all of that divided by the concentration of N2, which is 0.921, times the concentration of H2, 0.763, and then we've got to cube that concentration. Now, this is math that you would have to use a calculator for, so I invite you to pull out your calculator and type in 0.157 squared divided by, and then I would encourage you to use parentheses, for open parentheses, 0.921 times 0.763 cubed. Be sure to get the correct thing cubed. And when you do, I get 0.060 for my value for K. There's another part to this problem. It says calculate the value for K if the concentrations are now different. If the N2 concentration is 0.399 and the H2 is 1.197 and the NH3 is 0.203. We'll use the same expression for K. This expression for K is good no matter what the concentrations are. We're just going to apply it under a new set of circumstances here. So the new circumstances are concentration of NH3, the product, 0.203. Make sure to square that. And then we're going to write the concentration of N2, which is 0.399. And we'll times that by the concentration of H2, which is 1.197. And because of the coefficient in front of the H2, we've got to make sure to cube that. Again, please be careful when you type this into your calculator. Take 0.203 and square it. Then hit divide by, open parentheses, 0.399 times 1.197 cubed. When you hit enter, you should get 0.060. Students, it is not an accident that you're getting the same numerical results. The value for K, no matter what the situation is for this reaction, is always going to be the same. The value for K for this reaction is always going to be 0.060. And I have to put a little asterisk here, provided that the temperature is constant. There is some temperature dependency, but we are not going to encounter problems that ask you to think about that, okay? The value for K is the same no matter what the set of concentrations is. Okay, back to our notes. Let's go to the next slide here. There is a distinction in terms that I want you to be aware of. When we say equilibrium constant, we're talking about the numerical value for K, which is always the same at a given temperature. There are several different sets of equilibrium concentrations that calculate to give you the same equilibrium constant. We just calculated 2. of those equilibrium sets, different sets of equilibrium concentrations. We call those sets of concentrations that are valid for a reaction at equilibrium an equilibrium position. Any valid set of equilibrium concentrations for a given reaction. You can have multiple equilibrium positions, but you can only have one equilibrium constant, which is the numerical value for K, and it does not change. All right. So we've calculated a value for K. In our example, the value for K was 0.06. What does that mean? Well, if in calculating K, you remember that it's a ratio of concentrations of products divided by reactants. If that ratio is greater than 1, that means that at equilibrium, there's a whole lot of products. If K is less than 1, at equilibrium, there's a whole lot of reactants. If K happens to be equal to 1, neither reactants nor products are favored. It might be spot down the middle where the concentration of reactants and products are the same. If our value was 0.06, we had a reactant-favored reaction, a reactant-favored equilibrium in that last example. Okay, I want to leave you with one last problem. For the reaction that shows the dissociation of water breaking apart, here's your balanced equation. The value for K at a given temperature is 0.0024. At equilibrium, it is found that the concentration of H2O is 0.25 molar, and the concentration of H2 is 0.08 molar. What's the concentration of O2 under these same conditions at equilibrium? I'm going to go back to the Jamboard to work this out. The first thing we're going to want to do is write an expression for the equilibrium constant K. So look at the products. There are two products in this equation, H2, which has in the balanced equation a coefficient of 2. So if there's a coefficient here, we got to make sure to make that an exponent in the expression for K. The other product is O2, and its implied coefficient is a 1. So you could write an implied exponent of 1, or you could just leave it blank. Most of the time, people leave it blank. There is one single reactant in the equation. So if it's written to the left side of the arrow, I'm writing it down in the denominator. It's H2O, and its coefficient is 2. So we've got to make sure to put the exponent 2. Now, in this problem, they gave us the value for K right off the bat. What we're going to do is plug in the numerical value for K that was given to us, 0.0024. And then we're going to set that equal to the concentration of H2, which was given to us, 0.08. And since in the expression we had to square that, we're going to make sure to square it, times the unknown, X, that's the concentration of O2. We don't know that one, so we're going to solve for it. And that's all divided by the concentration of H2O, which was given as 0.25. Time to pull out the calculator. We're going to take 0.0024 times 0.25 squared, and then divide that result by 0.08 squared. So my math that I type into the calculator is going to look like this. Make sure to type it with parentheses. I encourage you to do that. I think it's very helpful. It often gives you the correct result. And we get a final answer of 0.023. And since they're asking for a concentration, I'm going to put the units molar, capital M for molar. Thanks for your good work. Good luck on the homework.